All right, I'm going to go to chapter 3 slides and continue from where I left off last time. All right. Can you see my chapter 3 slide page? Can
Yes,
you?
sir. Yes, sir.
Okay, all right. Let me review a little bit now that we have gone about more than half of the material. We talked about octet rule and describe the chemical reactivity of elements. Describe the features of ionic covalent bonds. We now know there are two different types of chemical bonds, ionic and covalent bonds. So we know ionic bond first. Then we also look at the periodic table and found out what groups of elements form anions and cations. And we know how to get their charges, cation and anion charges. We also know how to name anions and cations. Idea is once you know the anion cation names, you can name them, formula and name them. Polyatomic also part of ionic compounds. Majority of ionic compounds are formed by polyatomic ions. Therefore, simple anions, cations are easier to deal with. Polyatomic ions, you have to remember the list of polyatomic ions we gave you. Then whole idea is to write the name and formula of ionic compound. Now today we going over covalent compounds. Idea is to contrast properties of ionic and covalent compounds. I'm going to go over this again. Recognize the characteristic of covalent compounds. What are the ways to identify ionic compound and a covalent compound? Ionic compounds are solids, consist of ions. Covalent compounds are normally liquids, low boiling liquids and gases sometimes. They have lower melting point than the ionic compounds. So one of the ways to identify covalent compounds and ionic compounds. Covalent compounds also contain, like ionic compounds, two or more types of elements. One thing you should understand now is covalent compounds are formed by nonmetals reacting with nonmetals. They both have large number of electrons. They share electrons and become noble gas octet electrons with their valence shell. Therefore, they become stable. Similar idea, ionic compounds loses or gains electrons to make cations and anions and achieving octet of electrons that way. One of the ways to show structures of ionic covalent compound is the Lewis structures. We went over that up to that last time, how to draw a Lewis structure. Lewis structure is based on the idea. Lewis model is based on octet. Therefore, when you form a covalent molecule, group of atoms, the valence shell should also have the octet, showing the octet. For cations and anions, we normally show monoatomic cations and anions, outer shell structure of the ion, which has octet of electrons. Either cation or anion both has octet of electrons. In covalent compounds, what we show is a structure where you can see 8 valence electrons for most of the main group elements, duet for hydrogen, and we're going to look into that today. We're also going to look into resonance structures today. I will come back and review it next time. Then we're going to look at the shapes of the molecules. Covalent compounds are molecules, they have bond angles, unlike cations and anions of ionic compounds. We use electronegativity to tell whether covalent bond is polar or non-polar. We go over that little bit. 1.9 greater than 1.9 ionic bond between 0.5 and 1. Between 1.5 and greater than 1.9 is ionic. We're going to look into this. We will also want to know how to tell whether a covalent molecule is polar or non-polar. So these are the characteristics we're going to talk about covalent compounds. I'm going to go to place where I left off last time and start from there. We were on Lewis structures. Lewis structures are the ways to show octet of electrons to valence shell using dot for electrons. If you look at the water has 2 hydrogen, 1 oxygen. Each oxygen has 6 electrons. 2 times 1. 1 is 2 times 1 here is total of 8 electrons. Can you see that hydrogen, each one has 1 electron on each one of them, plus 8 valence electrons. When you write down the Lewis structure, there are 8 electrons. Each bond is 2 dots. So therefore, total of 8 electrons. This shows oxygen has octet, hydrogen has a duet. That's how the Lewis structure shows. Lewis structure basically shows the number of electrons in the valence shells of the atoms making up the molecule. If you look at ammonia, how many valence electron nitrogen has? It's 5A group, therefore 5 valence electron. Hydrogen is 1A, therefore 3 times 1 is 3. If you add this up, 8 valence electron. Nitrogen is the central atom, like we described here. We connect the hydrogens to the central atom here with 3 bonding electron pairs. So this is the Lewis structure. Lewis structure shows 8 electron pairs. Each bond is 2 electrons, therefore total of 8 electrons. That's the correct Lewis structure for ammonia. It shows the octet rule for nitrogen and duet for the hydrogen. Methane, 4 electrons here. Group 4A, 4 electrons from each hydrogen, therefore 8. This has 8 electron pairs. Each one has 2 electrons. We normally write a dot line or dot for electrons. So how many lines are there? 4 times. Each line is 2 electrons, 8 electrons. That's our issue. HCl. HCl has 1 plus 7, 8 electrons. Now all the hydrogen cannot have more than 2 electron duet, then rest of the electrons are going to be on chlorine. There are 8 of them. This is octet rule in the middle. Hydrogen has duet in all cases. There are other compounds, organic compounds. This is called ethylene. Ethylene is a gas that we use to ripen fruits. In grocery stores, we have gas chambers. We put the raw banana, green banana, then they get ripened. So this compound has a double bond. Double bond is 4 electron pairs shared between carbon. So the structure is this. This double bond has 4 electron pairs. This has 2, this has 2, this has 2, this has 2. That's 8 plus 4 is 14 valence electron. Carbon has 8 valence electron, both carbon atom. This is a hydrogen has duet. Because hydrogen is in the period 1, which has only 1s orbital. So there's another organic molecule commonly used in welding, acetylene, oxyacetylene, burn in oxygen. Acetylene is used in welding. This has a triple bond between carbon atoms. The structure is this. Therefore, if you look at this, there are 10 electrons. There are 5 electron lines. 3 lines is a triple bond. 2 lines is the single bond. Triple bond is 3 bonds at the same time. First one is a single bond, second one is a double bond, third one is a triple bond. So altogether it's called triple bond. Formaldehyde has the connectivity of oxygen and hydrogen like this. If you fill the octet to this, you get the Lewis structure. This is the Lewis structure of this. Therefore, it has, if you count the number of electrons on the Lewis structure, this is the octet, this is the octet, that's a duet, total of 12 electrons. That's how you get the Lewis structure and tell how the atoms in the molecules are satisfying octet rule. Carbonic acid, normally listed as H2CO3, has the structure of this one, H2CO3. There are 2 acidic hydrogen. The octet is complete on oxygen, carbon, and all oxygens. Hydrogen has a duet. The sum of the lines and dots representing lone pairs and bond pairs adds up to 24 electrons. That's the sum of the valence electrons. That's 6, 2, 6 times 3 is 18. If you add this up, this is 24. Okay? That's how you get 24 valence electrons, carbonic acid. Now we're going to go with a few more problems. Which molecule, covalent compound or molecular compound is same, have the structure that has 10 valence electrons? Start with this. Hydrogen is 1A, 1 electron. Carbon is 4 valence electrons. Nitrogen is 5. When you add 1 plus 4, you get 10 valence electrons. So that's the correct answer. A, not. This one has 8 valence electrons. We gone over. This has 8. This has 4 plus 6 times 2 is 12. 16 valence electrons. Therefore, answer is A. If I ask you how many valence electrons a molecule has, covalent molecule has, you can count the valence electron in each one of them and add them together to get the total. If you have ion, like a ion is 1 electron less. If you have a carbonate ion, for example, to get the valence electrons, you add them up and add 2 more. When you have ions, these are neutral compounds. You add or subtract, depend on add for the anion, subtract from the cation. Let's look at the Lewis structure of this cation. That's what I was going to tell you about. NO2 plus. This is the connectivity. Nitrogen is the central atom. This has 5 electrons. Oxygen has 6. 6 times 2 is 12 minus 1. Why minus 1? Because this charge is positive 1. Therefore, molecule has lost 1 electron. So this adds up to 16. 5 plus 12 is 17 minus 16. That's 16 valence electron. Now, how do you put the valence electron here? You put the double bond here, 2 valence electron. That's the octet is complete here. Octet is complete here. Then you put 3. I'm sorry, the total molecule is positive 1. Therefore, what is the description of this? 2 double bonds, 1 double bond, 1 single bond, 12 non-bonding electrons. How do you get 12? There are 6 of them. 1, 2, 3, 4, 5. There's a 1 here. So there's no, there's only 2 here. That adds up to 6. 6 times 2 is 12. Therefore, answer is B. Do you have any question about this?
No, sir.
There are 16 valence electrons. You try to get all of them octet. Yeah. So then answer the question. There's one double bond, 1 single bond. That's a single bond here. That's how you get. How many non-bonded electron pairs are in the Lewis structure below? Lewis structure is this. What are the non-bonded? This is here, this is here, this is, there are 8 electrons, 4 pairs. This is a double bond, this is a double bond, therefore 4 electron pairs. 4 is B. That's how you get it, B. All right. The chemical formula, that's formaldehyde. We talked about that. How many valence electrons must have? Formaldehyde is, we discussed this before. There are 4 electrons here, 2 electrons here, 6 electrons here. That adds up to 8 plus 6 is 14. 6 plus is 12. I'm sorry, 12. There should be 12 electrons. If you put 2 electrons here, octet is complete. Now this is the correct Lewis structure. Duet to hydrogen. Hydrogen has duet. Carbon has octet. So therefore, this is how I got the numbers. 1, 4, 6 valence electron. This is the Lewis structure. Another way of showing the Lewis structure. So it has how many valence electrons? 12. C is the correct answer. Do you see how I get Lewis structure valence electrons for the formaldehyde? The ammonium ion, how many valences must be shown in the Lewis structure? This is 5 plus 4, 1 from each hydrogen atom, -1. Why -1? The charge is on positive. That means lost electron. Therefore, 8 valence electron. How many valence electron? Sometimes we ask how many pairs. This is how many. This is the answer. C. Cyanide ion, hydrogen cyanide here. 1 from 1 hydrogen, 4 from 1 carbon, 5 from nitrogen. Nitrogen is 5A, carbon is 4A. They give directly, group number gives the number of electrons. Therefore, this is 10. 1 plus 4, 5. 1 plus 4 plus 5 is 10. So answer is C. So I added up, this is the Lewis structure. Central atom is carbon. Then you try to give a octet to this nitrogen to get an octet, you put 1 electron pair. Now all atoms, nitrogen have octet, carbon has an octet, hydrogen has a duet. That shows Lewis structure is satisfied with noble gas octet or duet for hydrogen. So answer is C. Based on the Lewis structure, typically form, I cannot see this. Let me. Carbon typically form 4 bonds. How many of you know that? Carbon Lewis structure is this. Normally carbon has 4s, 4p2. But normally when carbon reacts, it forms 4 lone pairs of electrons. Therefore, 4 bonds can be formed. B is the correct answer, carbon. That I wrote the same thing. The ethylene has this formula. You remember we talked about double bond is in the ethylene. That's the ethylene molecule. So answer the question. It has only single bonds. No. Ethylene has 1 double bond. That's true. Ethylene has 1 triple bond. No. Acetylene has. None of these correct is wrong here. Answer is B. Acetylene, we wrote down acetylene. That one. Which of the following is correct distribution of acetylene? Acetylene has 1 single bond. There are 2 single bonds. Acetylene has 1 double bond. That's not true either. This is not true either. Acetylene has triple bond. That's true. None of these. Answer is C. Do you see in the Lewis structure, you can see acetylene has octet here. Carbon has octet, duet for the hydrogen. That's the main idea of Lewis structures. Answer is C. Again, we are asking, this might be separate problems, not connected to 165. He already talked about acetylene. So which one is the Lewis structure? Which one of these Lewis structures best describes acetylene? Lewis structure should show octet and duet. These are chemical formulas. These are not Lewis structures. They are not Lewis structures. The Lewis structure should show the number of electrons on the valence shells of the atoms combined in the molecule. Now, exception to Lewis structures. Because these 3 elements, hydrogen always shows a duet because it cannot have more than 2 electrons in the oneness from the first period. These elements come from helium also never get octet. Therefore, it's an exception. Lithium also when it forms ions, its outer shell has 2 electrons, similar to helium. Beryllium also forms several compounds which have 4 electrons because lithium has 1 electron, beryllium has 2 valence electron. It normally shares with other like beryllium hydride. We're going to talk about that. Therefore, there are exceptions to Lewis structures. Lewis structures are based on octet rule, but they are not behaving like octet. Period 2, starting with lithium, beryllium, that use these orbitals follow octet rule. Beryllium, boron, carbon, nitrogen, oxygen, fluorine, they all follow octet rule. These 4 orbitals contain maximum 8 electrons, hence octet rule is obeyed. But period 3, which can have, in addition to 3s, 3p, 3d atomic orbitals, therefore 2 electrons here, 6 electrons here. Sometimes it gets 2 more or 4 more, leading to 10 or 12 total number of electrons. I describe it here. There are 9 atomic orbitals, then accumulate more than 8 electrons. 3D third period has d orbitals that could be filled. Therefore, they show compounds having more than 8 electrons, 10 or 12 in the valence shell. So let's identify some of these. Phosphorus is a third period element. This is the normal, the 8 electrons. That's okay with octet rule. This one has phosphorus pentachloride, has 5 bonds. There are about 10 electrons. This is the exception to Lewis structure. Octet is the Lewis normal description. Therefore, 10 electrons is the exception. If you look at this one, this has also 10 electrons right here. If you count around here, 10 electrons. 1, 2, 3, 4, 5 lines. 5 times 2 is 10. Sulfur also is a second period element. Third period. This is third period. This is third period. Also a third period element. So this is the normal form of octet is there. But this one got 10. This one got 12. You see that 10, 12, because d orbitals can also 3d orbitals. Therefore, periods greater than 2, period 3rd, 4th, 5th elements form compounds with more than 8 of electrons, sometimes 10, 12, 10, sometimes 12. Now, if you look at the NO molecule, this is an exception for another reason. There's 5 valence electrons on N, 6 valence electrons. 5 plus is 11. Now, when you pair up electrons on the nitrogen like this, there's always 1 electron left over. You can 1, 2, 3, 4, 5, 10 plus 1. Therefore, it has a lone pair of electrons or unpaired electron. This is never going to satisfy octet rule. So, NO contains an unpaired electron. Following this, that's because the way it is distributed, contains 5 unpaired electrons. No. Contains, we don't talk about this. Contains unpaired electrons is the answer. It's an exception to Lewis structures. Which of the following elements contain electrons more than 8 electrons associated? This is period 2. This is period 2. This is period 3. Period 3 has 3d orbitals. There's a possibility of forming structures with phosphorus that has 10, 12 electrons. Therefore, answer is C. In a Lewis structure, which of the following atoms can have more than 8 electrons associated with it? More than. Is sulfur. That's a 3D. This is the second period. This is also first period. It's more than. This says less than. If the question was less than, okay, hydrogen should be the answer. Answer to this question is D. Which one Lewis structure contains atom that violates the octet rule? If you write down this obeys octet rule, this one doesn't. That's a beryllium. Beryllium would form like helium structure. That's a less than an octet. So this is PCl3 is correct. This one is correct. This one is if you write down 2 chlorines, 3 choline. These are the Lewis structure. This is the correct answer, B. Recognize the bonding characteristics. Do you have any question? Do you guys have any question?
No, sir.
Recognize the bonding characteristics of covalent compound. There are 2 types of covalent compounds containing covalent bonds. One is the non-polar covalent compound. Electronegativity difference is between 0 and 0.5. 0 and 0.5. We talked about that. Polar covalent bond is 0.1.9 between. Greater than 1.9 is ionic bond. We talked about this. Difference in non-polar compound, that's the less than. This is less than 0.5. That's right here. Between, that's a polar covalent bond. Greater than is ionic bond. When you have 2 elements, you can decide whether that compound is going to be ionic or covalent. If it is going to be covalent, the bonds between those 2 atoms could even be predicted. Bonds going to be polar if the electronegativity difference is between 0.5 and 1.9. If not, if less than 0.5, between 0 and 0.5, that's a non-polar covalent bond. That's the same answer, that is polar covalent is that. Now we're going to go over naming ionic covalent compounds. We go now naming ionic compounds. Ionic compounds are named based on anions, cations name. But there's similarity between naming covalent compounds and ionic compounds. But the main similarities, it sounded the same name, but we don't use prefixes in ionic compounds. Ionic compounds, formula is obtained by cross-multiplying charges to get the charge balance. But the covalent compounds don't have charges. Therefore, you have to tell exactly how many carbon atoms going to be, non-metal atoms going to be on the molecule. Covalent compounds are mainly produced from non-metals, between non-metals. The electronegativity difference is less than 0.5 or between 0.5 and 0.19. Non-polar covalent bonds and polar covalent bonds are formed. So when you're naming sulfur and oxygen, this is, if you look at the periodic table, this is less electronegative, S. Therefore, sulfur, you have to tell sulfur dioxide. In ionic compound, we don't do that. Sulfur oxide normally. But covalent compounds, you say sulfur dioxide. Same thing, first name is the same name as the element sulfur dioxide. Prefixes are used. Di, tri, tetra, penta, hexa, hepta, etc. Mono is omitted. Mono, sometimes you use carbon monoxide. For the first atom, you don't call this monocarbon monoxide. It's called carbon monoxide. Carbon monoxide. First element, mono, is never written. Second atom is carbon. That's the example, is carbon monoxide. Nitrogen oxide, common name is. There are two forms of nitrogen oxide. This is called nitrogen monoxide. Nitrogen monoxide is also called nitrous oxide, nitric oxide. Sulfur dioxide, there's no problem. There's a systematic name is with the element name and the number of atoms given by prefixes. How to name a covalent molecule? Name each of the covalent molecule. What do you say? Systematic name. Nitrogen dioxide. Nitrogen is the first name. Oxide is the second name. Nitrogen dioxide. This is what?
Dinitrogen.
Tetroxide.
Yeah.
The first name, non-metal name by first nitrogen has, it keeps the non-metal name, nitrogen. The second, with higher electronegativity, the oxide. Between nitrogen and oxygen, this is greater. Oxygen has higher electronegativity. Therefore, first nitrogen is written, dinitrogen tetroxide. What do you say? Dinitrogen tetroxide. Nitrogen dioxide, dinitrogen tetroxide. Do you see how you name covalent compounds? We don't use prefixes in ionic compound. That's the main difference. Prefixes are not needed. Ionic charge will balance the formula. When we name binary compounds, which of the following is true? Element that has more atoms in the molecule is written. That's not the. What is the rule? Element with higher lowest electronegativity. Alphabetical order, that's not the way. Name less electron negative element first. That's correct. We name the more electronegative, that's wrong. Therefore, answer is C. Do you understand what we said in the previous slide? The question is about which elements name first. What is the correct chemical name of the compound with the formula? What is this? This is a covalent compound. These are non-metals. Therefore, you have to use prefix to show the number of atoms. What is that? Trioxide. Tri means, do you know Roman numerals? 3, 4, 5.
Yes, sir.
We listed that on one of the slides. Mono, di, tri, tetra, penta, hepta, octa, nona, deca. So this is the correct answer. What is the name of, this is non-metals. These are covalent compounds. They have molecules, Lewis structures. What is the name of this one? Sulfur is the, if the formula shows that is true, we use the formula in the formula. First element has the lowest electronegativity. Sulfur has lowest. So sulfur, what is the correct answer? Sulfur dichloride. That's the. Are you guys there?
Yes, sir.
Do you understand the question?
Understand.
Okay. This is the correct answer. Systematic name is following the rule. Common name is kind of a nitric oxide, nitrous oxide. We normally don't, you have to exactly know what the common name is. This is carbon disulfide, systematic name. Carbon disulfide is here. That's the correct answer. Which name is, formula had the name dinitrogen pentoxide. This has to be 2 nitrogen, 5 oxygen. So what is the correct answer?
A.
That's good. Which of the chemical formula dinitrogen tetroxide? Right? Is the correct answer. Okay, I'm going to change the topics now. We go now naming chemical compound, covalent compounds, and also go now, previously go now Lewis structures, and how we show Lewis structures follow octet rule, sometimes exceptions. We also talk about. There's another important idea that came up. The Linus Pauling is a famous chemist, American chemist, who won 3 Nobel Prizes. He's the one who came up with the protein structure, helix structure for protein. He's very famous to have 3 Nobel Prizes in chemistry. Now, if you look at this molecule, he wrote the Lewis structure for carbonate ion. When you look at the Lewis structure, he found out this carbonate ion has a double bond in the one carbon-oxygen bond. This is a double bond here, but single bond. But in reality, carbon bonds are equal. All carbon bonds have same length. It's less than double bond. It has a single bond has 1 electron bond. Double bond has 2 electron bonds. It shows 1.5. This is kind of in between. To explain this idea, why the bonding is all same, he came up with the idea. When you have Lewis structures where a double bond could be distributed, this double bond could be distributed between 1 here, 1 here. There could be 3 Lewis structures could be written down. That's the third one missing. I didn't do right. I will show you again. This idea about this is the description. Many molecules and ions are best described by writing two or more Lewis structures to describe the properties. One Lewis structure won't show the proper. The real molecule have hybrid properties. So these are concept of the real molecule. These are not real one that exists, but the real molecule is mixture of these two, hybrids of these two. The contributing structures Linus used was called contributing or hybrid structures. Double-headed arrow, when used in between two Lewis structures, show the resonance between the real structures between these two. It's like a donkey and a horse. Donkey and a horse. What do you get? Mule. Mule is neither donkey nor horse, but it has both properties. This is the same idea. Now molecules behave like donkeys and horses. This is strange. Now some molecules you need to use more than one Lewis structure. This idea is important to describe bonding in organic molecules later on when you go to take organic chemistry. Double-headed arrows are placed between individuals. The molecule is a resonance hybrid of various contributing structures. There are three contributing structures for carbonate ion. So double-headed arrows means you take the electron pair here, put in between and move that electron here. Curved arrow, not double-headed arrow. The curved arrow is, you get that one. When you move electrons here, that's how you get this one. So from this one further, you can move that here. Let's talk about that in a different. The curve arrows are used to move the electron pair to adjacent atom. Here, that's how we use. You can get another. I cannot see this structure here, but you can get another structure. I will show you. Curve arrows are used by Linus Pauling. Carbonate ion. I'm writing it again. Do you see these arrows moved here?
Yes, sir. But I don't understand it.
You don't understand?
Yes.
Now, when you move that one, double bond goes there. Right? There are three structures where the double bond is in different places in the molecule, right?
Yes.
That's the resonance. There are carbonate ion. You have three resonance structures. The bond is not a single bond or double bond. They are a mixture of double bond and single bond. Bond length is 1.5. If a single bond is 1, double bond is 2. This is less than 2. This is greater than. Therefore, real molecule, to explain, you had to write three resonance structures, hybrid structures. The real molecule is hybrid of these three. They are not real ones, but the concept of mixing up, like I described about hybrid between horse and a donkey is a mule.
Mhm.
The resonance in SO3 molecules. Similar idea. Same as carbonate ion, SO3 molecules also shows resonance. There are three ways that double bond could be distributed. Right here, right here. Therefore, real molecule is representing all the features of these three. So that's how what the resonance is. Do you have the idea what resonance is? It's used in double compounds with molecules with double bonds when they can be distributed in more than one place, three places in the sulfur dioxide and carbonate ion. They contribute to three hybrid structures. All these are the criteria for acceptable contribution structure. All contributing structures must have same number of valence electrons. That's true. We didn't remove electrons. We only reshuffle. They still obey the octet rule. No more than 2 electrons in the valence shell. If the molecule has hydrogen, it cannot have more than 2 valence electrons. That's normal Lewis structure. This is the octet duet still hold. In resonance structures, applying to compounds with more than 1 electron, 12 electrons, 10 electrons, 12 electrons. You can have up to 12 electrons in the resonance structure of the phosphorus and sulfur. They differ valence electron distribution. Position of all nuclei must be same. We never change carbon or the oxygen. That's the idea. Have same number of unpaired electrons. We never change any unpaired electrons. They have the same number of paired electrons. Now you can look into different structures and say whether there could be resonance hybrids following these rules. What symbol is used to show the resonance structures? What did you use? That one, double-headed arrow. This is a little different from any. This is the forward reaction, backward reaction, equilibrium reaction. This is used between two Lewis structures to indicate their resonance hybrids. D is the correct answer. Which of the following is true of individual resonance structures that contribute to a resonance hybrid? Based on criteria we go over, each resonance actually exists? No. They are part, the real molecule, they are our creation to describe the properties of molecules, covalent molecules. We don't know about these. They are not really exist. We don't know. In going from one resonance structure to another, electron move from one location to another. Why this is not true either? Because there's no resonance structures. Our description, they don't exist. We can show on the paper going from one resonance structure. This could have been Which of the following are the two individuals contribute to a hybrid? Why this is not true? In going from one resonance structure to another, the electron moves from one location to another. That's kind of a true. So I will look into this and talk about next time whether if it is the correct answer. In student is attempting to draw several resonance structures for SO3. Which of the following are allowed? Change in the number of valence electrons? No. You cannot change number of valence electrons. That's not true. Change in the position of the valence electron. That's possible. Like here we have this problem. The change in the number of protons and neutrons? No. Nuclei are never changed. Atomic nuclei are not changed either. Therefore, only B is the correct answer. All right. Which of the following regarding individual resonance structures that contribute to a resonance hybrid? This is not true. They are not the equilibrium. They are our concepts. Each resonance structure is less stable than the resonance hybrid. Resonance structures of the resonance hybrid differ only position of valence electron. This is the false answer. This could be true. That's one. Each resonance structure is stable than the resonance hybrid. The position of atomic nuclei is in the resonance. This is true. That's the only one is A that we got right. Which of the following is true is carbonate ion resonance structures? This is the carbonate ion. Carbonate atom does not have octet. It does have octet. It's all carbon, oxygen have octet. Total valence electron 24, that's correct. When you added up all dots and lines with 2 electrons, it added up to 24. The electrons are constantly moving from one bond location to another. Now that's the idea. I think we thought it was correct. They are distributed according to our hybrid, but they are not moving from one location to another. None of these. So I had the C as the answer. Minus 24 electron, that's true. That's, I said true. This is wrong. I got it wrong. True is B. What I'm doing, I said this is wrong, but I said the B is the correct answer according to what I pick here. B is the correct answer. Now, covalent molecules, covalent compounds have shape. Molecules has, for example, water has a shape. So how do you get the shape of a covalent compound is the idea that we're going to go over. We use a model called valence shell electron pair repulsion theory. When you look at the valence shell of an atom, the last electrons are distributed around the atoms making the Lewis structure. So therefore, these electrons will repel between each other and make the shape. For example, if you take the water molecule, there are two lone pairs in the Lewis structure. The four electron pairs repel each other in the central atom. Central atom makes the molecular shape. So it will be in a tetrahedron. Then therefore two hydrogen going to be angular because those lone pairs repel. This is the idea. Lone pair electron repulsion of electron in the central atom make the shape of the molecule. Valence electron of atom may be involved in forming single, double bond and triple bond. Can be unchaired, lone pairs of electrons. All of them count similarly, whether it's a single bond, double bond, lone pairs. But double bond has more electrons than single bond. Therefore, it repels little further than single bond. Triple bond repel more than double bond or single bond. So all electron groups, single, double, triple bond, are considered one unit of repulsion. Because like charges repel each other, because the electrons are negative, various regions of the electron density around the atom spread so that it is as far away as possible from each other. Let's look at methane. Methane has this structure. How does four things arrange in space equally distant from each other? That's tetrahedral. Tetrahedral angle, perfect tetrahedral. How many of you heard about tetrahedral shape? Tetrahedral shape. There are shapes, angular shapes, stuff like tetrahedron is four corners, four edges. Angle is 109 because four things distributed in space form angle of 109. What is the angle between carbon, hydrogen, and methane? 109. Tetrahedral angle. That's the valence electron repulsion theory. Ammonia has this structure. What do you think the structure is? There's a 3 hydrogen, 1 lone pair, according to Lewis structure. The lone pair also, we don't see a structure there. Electron cloud repel other 3 hydrogens down. Therefore, it is less than 107. Do you see 107, 109 should be the right tetrahedral angle? Why ammonia is 107? The lone pair repels a little bit more. Therefore, this molecular shape is called triangular pyramidal, triangle base, and a pyramid or pyramidal. Pyramidal is named for this shape, pyramidal or triangular pyramidal. This is less than 105. Pyramidal, trigonal pyramidal. There are 2 names for ammonia. Water. Water has four electron pairs. 2 bonding electron pairs, 2 non-bonding electron pairs. It's based on tetrahedral electron repulsion idea. But the 2 electron non-bonding electron pair, in ammonia you had only 1. Therefore it pushed down 109 to 107. But in water there are 2 lone pairs of electrons. It repels bonding electron pair further. It contracts from 109 to 104, 4.5. So this is called angular Ammonia molecule is called triangular pyramidal or pyramidal. This is called angular or bend. Bend or angular. Bend means like elbow. Why it is 104.5? Ammonia is 107. 107. Ammonia got only one lone pair. Water got two. It pushes down the 109 further. It's pretty easy to tell the angles between atoms in a covalent molecule. We already know the Lewis structure of this. This is the how many electron pairs are in here? 3. I told at the beginning, single, double, triple, and non-bonding have the same effect, except triple bond has more pushing than double bond or single bond. Lone pair has more pushing other electron than single bond. So this is 3 electron pairs, trigonal planar. This is trigonal planar. Whole molecule is planar. This is a planar molecule on the side. So ethylene is planar molecule. Ethylene is planar molecule. How about acetylene? Acetylene has 3 double bonds, but 1 triple bond. This is counted 1, this is counted 1. Therefore, linear. 2 things equally away from each other is linear. It's a linear molecule. Side view, you can see like a dark. That's a linear. Acetylene is bond angle is 180. Ethylene is 120. This one is 120. Why this is little bigger than 120? Because this double bond pushes rest of it, these two further. Even you can explain minor variations. So tetrahedral angle, based on tetrahedral angle, methane gets tetrahedral structure, ammonia gets pyramidal or triangular pyramidal structure, water gets bend structure. Planar structure. Both formaldehyde and this is trigonal planar, this part, therefore planar molecule. Linear molecule, carbon dioxide, has 2 electron pairs, double bonds, 2 electron groups, therefore 180. If I ask you what is the bond angle between, what is the shape of border? Shape of border is angular or bend. Ammonia is pyramidal or triangular pyramidal. Methane is tetrahedral. Ethylene is planar, 120, close to 120. Acetylene and carbon dioxide is 180, linear molecule. The angle between this is 180. This is 120. This is tetrahedral. Ammonia is close to 107, water is 104 because the lone pairs changes the angle. Which of the following is classified as a group in the valence shell electron pair repulsion theory? An atom, we don't talk about atom repulsion, a lone pair of electrons and valence electron, either an atom or valence electron. Which of the following group is valence shell electron pair repulsion? A lone pair of electrons of atom. A valence electron, we don't talk about valence electron individually. one of the group is lone pairs. I didn't see the either an atom or lone pair. We look at the atoms also. I didn't understand the question. Atom also shape is related by valence shell electron pairs plus the atom. That's the angular geometry is associated with molecule which is central atom has two bonds, and angular geometry is associated with border. Border has two non-bonding, bonding, bonding, two bonds, and first one, two bonds and two non-bonding electron pairs. That's the correct answer. More than that's also correct. Two bonds and one non-bonding, that's not correct. Two bonds and no bonding electrons. Central atom has two bonds, bonding electron, bonds, and non-bonding electron. First one, two non-bonding, one non-bonding. Two bonds and no non-bonding electron. Okay, I got it. If you have that's angle, if you have this lone pair bonds, this is also two bonds, one non-bonding. That's also has angular shape. Therefore, answer is two bonds and one non-bonding. Because if you have a triangle, one become non-bonding, it become angular, right? Therefore, two correct answers. This is kind of tricky. I'm going through this because you have to show the complexity of stuff to understand it. What are the bond angles in tetrahedral geometry? You can answer this question. What is the tetrahedral geometry angle? Tetrahedron 109. Remember, methane has perfect tetrahedron 109. Is C. Valence shell electron pair repulsion VSEPR theory predicts that geometry of the is. Now, nitrogen is NH3. PH3 is same group, therefore same Lewis structure. Lewis structure of ammonia is trigonal pyramid or pyramidal. Therefore, PH3 should be same. Trigonal pyramidal or pyramidal is the C. We use periodic table to get the same Lewis structure are formed by same elements in the group. Which of the following molecules does the carbon atom have a nearly tetrahedral distribution in electron density? Which one? C2H6. C2H6 has structure. There are four bonds here. Therefore, it says tetrahedral. Acetylene and ethylene has double bond, triple bond, and a double bond. Therefore, they don't have tetrahedral. Answer is C. Which of the following molecule does the carbon atom has a nearly trigonal? Trigonal plane is B. Remember ethylene we talked about? I'm going to finish this after. Which of the following carbon atom has linear distribution? Linear means acetylene. So these gives different angles. Trigonal plane is 120, is C. Question 231. Linear distribution is 180. The answer is D. Ammonia is, what the angle in ammonia? 107, B. It's deviated from 109. Water molecule has 104. That's the predict the bond angles of the carbon atom in carbonic acid. 1 to any. Carbonic acid has trigonal planar, 3 bonds in the carbon atom. So we are done with the predicting geometry and the angle. Even those quantities. Okay, you guys been good. Do you have any questions or anything? All right. See you next Wednesday.
Okay, sir. Thank you.
We will see you on Wednesday. All right.
Okay. Thank you.
Thank you for coming. Take care.